All right, let's do the next step. Excuse me, do the next step here. So I want to do I'm going to just set that aside, kind of sketch out what the next step might look like. I'm going to want to do something like this, I suppose. Although, I have to decide if I want the tokens to be explicit or implicit, essentially. Right, are they going to be explicit in the API? Or you have to go like Lex, arena text, and you have to go tokens, and so then you have expression token array tokens, right? And then I want to test a few different kinds of things. I need a plus b plus c plus times a plus a times b plus c, and I want to include equal signs and right to left. So we can have things like 1 plus 2 equals this. Maybe we could do it like this. So there we go. That does that. That tests precedence between those. The equal signs test precedence. This tests that. Okay, so then that tests that, and then that can test parenthesization that way. And that way. Okay, so that doesn't actually. What I guess I would have to do is do that. Okay. And no, all this isn't supposed to mean anything. It's just a bunch of different test cases in a big single expression so that I can see what it looks like when it comes out. Now I have to design a data structure for the output of the parser. But the parser functions are basically going to be something like what's the output of this? It's like a parse node, I guess. And that's my mistake. That's the struct. But I meant to be doing parse. Yeah, okay. Parser types. Okay, all right, I'm okay. I choked on some water, but I'm okay. So, yes, just I think this is the signature I'm gonna go with for now. So, except maybe I'll switch these around, like the tokens is sort of dependent on the text, so it's more appropriate. Okay, so then parse node. What are you gonna look like? You have to tell me. I guess for now what we're doing is just a strict binary operator tree with then leaves at the bottom, right? So each node is either a pair with an operator. Each node is either a pair of nodes together with an operator, or it's an ID num token, right? So we get a node kind, operator, ID num. Maybe I'll call that leaf in this context. And I'll add a null there. Count. I'm going to anticipate that this is going to become an X list. And just do that now. We'll do it this way for now. Oops, I'm bumping the mic still. I should reposition it. So I do that a little less. Hopefully that's okay. So what we're really going to need is we are going to need like operator kinds. This is going to be the operator, and this will be the leaf, which will just be a token index, right? I suppose I could keep the token index. It's just that it's not really what you want. So okay, so now that we know what the node is, let's define the parse or the operator kinds real quick. So these are currently just going to be this fixed set plus mul, I guess times, plus times and a sign, right? Seems like a good setup. So We've got that. Yeah, okay. So that's the node type. Now, let's see about implementing that parser. Okay. In order to do this, I'm going to need to write down a grammar, because I really don't know any other way to sort it out. Where did the... Okay. So I think it's going to be something like an assign going to be an x and it equals x. It's if I want it to match this like this, then I make it like this, right? Where that can be that or that. So we see the next thing, and then if there's an equal sign, then we find a whole other assign there. I think that works. And there's the times. So the times is the thing that actually is going on here, the next level below. And then this is like x times x. I should put it, I'm going to put it in quotes whenever it's like literally naming which operator. So operators will be matched against these single quoted things here. So times is like the next thing down, times one of itself. We don't want to write it like this because we don't like that recursion on the left that creates. Instead, normally the way I go about thinking about it when it's in this case, I think, is I go like this. I'm going to have it repeat however many times it wants. That could probably work up here too, right? This is just the generic way to say you don't want to build your precedence into the grammar that you're using to sort it out by hand. I think that this works for both, and I'll just I'll see when I get close if I can put them together in the right order or not. So this becomes a plus times a bunch more pluses, and this becomes a leaf plus a bunch of leaves if you want, and then a leaf is either an open parenthesis and a sign and a closed parenthesis. This actually simplifies down to this. Or an IDnum, which is just a token type. Right? This seems to me like the appropriate by hand grammar to get this off the ground. So I think what I would prefer to do though is just skip straight to doing this with a precedence table, because as I'm thinking it through, this is going to get a little bit muddy and repetitive anyways, and maybe it would be more fun to just cut straight to it. It's kind of like skipping a step because you don't, it might be yeah, I don't know. You might be biting off more than I can chew in one go by doing this, but it kind of feels like I might be able to pull it off, and I want to try. So let's give it a shot. I'm going to skip straight to setting up a precedence table. So what this does is, instead of having all of our operators look like separate parts of the grammar and implementing precedence that way, we instead define into the model now a discrete ordering between precedences. And so you get things like, well, in this case, we're going to have a precedence for each of these operators we already have. And I'm not quite sure if I want the higher or lower number to be the higher or lower precedence level. That's a little bit of a difficult issue, but what I then want to do is I want to be able to assign information about each of these. But man, doing this without C scripts is going to suck. So I guess I'm going to start C scripting this actually. Let's see. I want to compare this to how I did other example headers here. Okay, so let's do a precedence and an operator symbol set. Right, so what we're doing is just taking the things that would have been enums in a or structured precedence table and skipping straight to making them symbol sets. So a precedence, I'm going to give it a name and the option to be right to left. Option to be right to left. Default will be left to right. So a right to left operator is like, just to clarify what I mean, left to right operator is like this one, where if you write a plus b plus c, you interpret that as this, right? Same as like if you wrote a minus b minus c, I suppose, right? You first group and apply the operation on the left, and then you take the result and apply it there, right? That's the way you imagine applying certain things like minus. With plus, it technically doesn't matter since it's an associative operator anyway. But the parser, like the definition in a lot of languages, still says it goes this way for whenever it matters, right? Or maybe it's just you need to pick something because you're writing a binary tree parser like we are, right? So that's what that one is, left to right. And so then when you write A equals B equals C, that is by default automatically equivalent to A equals B equals C. Because if it were the other way around, you would, these are assignments, right? So it's like this one means take C and put the value of C into B and then put it into A. If you had put it the other way around, which is what this is supposed to mean, right? A and B both get modified to equal whatever C equaled at the beginning, right? It's an assignment to both. So yeah, that's the C way of doing things. That's what I'm recreating today. So we have a right to left operator in the assignment operator, and the other operators are left to right operators. Good, and then the precedence then is like whoops, I'm copying too much from hook point. I don't need the hook point struct code. I just need the define precedence part. So there you go. You define a precedence, and we're going to say if you want to. How do you spell that? Is that forgetting how you spell this? I don't have it in any of my examples yet in C scripting. I'm also going to add this into the base layer. There we go. Okay, so I don't have any instances of this. I think that's the right way to spell it. Oh, it's good that I've got one. I'll just leave it at that and try it out. So precedence needs to know name, and if it's right to left. And the operator so each operator here, I guess I'll put the prefix on all this stuff still, though I won't cut that out. Oh, I didn't finish the boilerplate. I need to go back and do that first. Okay. Give me something to copy from. So here we go. This is the piece I skipped. SM frame becomes expression precedence. Precedence. We all agree. Precedence, right? Precedence. Okay, good. Frame precedence. This becomes precedence. So each time we create an operator, what we do is we assign it to a specific precedence. Okay, this should be enough. I think that's about the whole thing. So then each operator gets a precedence. That'll be fine. Okay. And then we need a sci init. Oh, I also need the definer macro thingy. So sci define xp operator n equals and then yeah, you have to say your precedence here. So this can then go precedence ID equals get the raw. We're gonna use a new line here. exp precedence on the p. Okay, and then if we are in a signing, then we're gonna sign it the expression operators. So I loop over all the operators and I fix up each of the precedence IDs. Okay. Okay, so that sets it up. We've got an operator and a precedence, and I should be able to work with this. So I think the way I imagine doing it is first we'll go and we'll define the precedences. Those are assign times plus, and then we'll define the operators. Right. And also, when I'm defining an operator, I want you to give me the, like, I don't know, the op text or whatever, the string. I'm going to stick that in there too. So this is going to be the token string. Token string equals straight const stir. So yeah, you just give me a string literal. I'll fill that in, and then set the precedence. So then this can become like equals times plus. Right. And then the only thing we're missing is an order between the precedents, right? In the sense that this whole symbol set system, I mean, there's two different ways you could go about it. You could embrace the fact that, generally speaking, the compilers pretty reliably put the global variables together into the data section where they belong in the order that you declared them in, right? That's what C compilers are doing because it just makes sense. Why would they do anything else? But there's nothing standard about any of this. So at some point you decide on how many non-standard assumptions you're building in, how you are working with it. And I've always built in the assumption that I don't know what order they're going to be in globally. Just to prevent me from making like a whole lot of investment into this in a way that's working 99% of the time, that if it does break once, might be really hard to recover from. It just seemed like that would be super subtle and frustrating if it ever happened, that the order stopped being predictable somehow. And that depending on it being in a specific order by the way order you write it in might not be the right thing to do at this very early stage of being able to program like this. Not that, like, eventually I would definitely want to have my data structure for the source codes to have both ordered and unordered interpretation being sort of given. Like, I would prefer to just be defined from the ground up that there's a way to get order control for this sort of stuff, so if in regions that you want to. You could create a list instead of just doing the gather thing that symbol sets do right now, like a closed version of a symbol set, perhaps you could call it. But anyway, the point is, right now it's not available. So there's a couple ways I could go about addressing that. I could, whenever I create one, just assign a number along the way, right? And then again, I don't know if it's 1, 2, 3, or if I need to flip the order here, but I could say, like, we're just assigning precedence numbers, and this is then telling me the numerical order, so that if these get written down in a different order for any reason, my IDs for them will still compare to each other through this, right? Now, a different way I could do it is to just, at runtime, arrange them into you know what? I like the first idea better because I like that it's. I was about to say I could arrange these into an array, but that doesn't give me the data structure that maps these IDs to their levels, and that's more relevant. So I think this is the way I'm going to do it. And I also want to make sure right to left is set to 1 on this one. And then we just do this like order. And we put an ordinal right here to give us the order on the precedences. And it's assumed that you're gonna put them in as just whatever makes them valuable or useful, but you're not going to ever do duplicate values, right? That's the most important thing here. You can do whatever else you want with it, but there shouldn't be duplicates. At least that's how I think it should be thought about. I guess you might also prefer to say that they should be contiguous, but I'm not sure that will matter. So then let me write a new grammar. Let me write a grammar that really more reflects the way that this code is going to work rather than the grammar itself, but that factors out all of the operator precedent stuff that was built into the first grammar. So we have an operator case, and when we have an operator case, what we see is a leaf and then a sequence of additional operators, essentially. So we see there's like an operator, maybe the token is called the operator, and this is the op, and then leaf happens again, and it can repeat any number of times right there. That's essentially what I think we see, right? We're going to come in and say, give me a leaf. Is there an operator here? Then the logic of how those nest with each other will follow from the comparison of the precedence levels. Yeah. We'll figure it out. Then a leaf is just going to be an open parenthesis or a closed parenthesis and more ops, or an ID num token. Right? Okay. So now what I do is I create these like helping out types. I guess I'll start with them not having any inputs or outputs, but this is going to be like parse leaf, and this gets the parse context, and maybe that's it. And then we also have parse op, right? I'm not sure if that's the signature I want for the parse helpers, but that might be fine. So what we're going to be doing is we're going to start off with the parameters. I'm going to want to be able to pass the arena through too. Parse context. And then we're going to be keeping track of which token index we're on inside. And we'll see what else we need as we go. So then the way this can work is you set up a parse context at the beginning of the parse function. It needs to know the text it's carrying through. It needs to know the tokens it's carrying through. It's already got the correct token index. And then you start parsing an op. And the reason it's op and not the other one is that if it were the other one, well, this tells you what's allowed to represent a whole expression. If it's this, then a whole expression is either a thing wrapped in parentheses or it's just a name or a number, right? But obviously 1 plus 2, like this, it's a fine expression too. So I prefer to be able to count leaf plus leaf as an expression. And since this includes leaf, right, anyway, it's like op is just the more general symbol in the grammar, right? So it just kind of works out. So parse op arena context, we'll figure out probably either returning the nodes we build as we go or constructing them here on the context and rating them off afterwards, but I don't know yet which. And then we got to implement both of these. So let's do the leaf part first. With a leaf, what we have to do is say, all right, if context token index less than context tokens dot count, and well, we don't have to do it that way because we have a terminator, so we can go if tokens dot tokens token index, and I guess for starters I would like to do if we see white space, then I guess we just need token index plus equals 1. I don't think there's anything else we would skip like that. I guess we could skip operator errors. I guess, but I think it's just better to turn that into a parse error and stop to make it simple. So yeah, since they get glommed on, I only ever have to increment once, right? There shouldn't be another token index. So there shouldn't be any need to, another token index with the same white space kind, right? So I think that should work as just the skip white space logic. And then we have to see check for open paren. Right, so we've got an open paren, then we should be able to consume that and run the logic for parse op, and that'll gather up whatever's inside those parentheses here at this vertex in the logic, and then and it'll advance the token index to the right point, so that we should then be able to say require a or error. Token kind close paren. Right. So there's the consuming the token. There's where we'll come back to get an error to you properly. So that's the check for open parenthesis. Now, check for ID num. Kind of feel like why not just do switch on this case. Open paren goes like this. Case. And here we emit a node. Right. So that's basically it for the leaf. I think I'm going to just do returning parse nodes through the functions. So this goes like this goes like this goes like this goes like this. And so this becomes like this. We've got the task of building a parse node, and then we've got just tidy this up so I can see it a little better. Yeah. You go there. And then, of course, token index plus equals 1 is still going to happen too. So here, the token index just becomes the information that lives on the parse node, because it's just like whatever number or variable name or whatever you put there, sort of the terminal case for constructing the tree, right? So you just build a node of that and stick that there. And then this is different. If I'm here, I've got something. If there's not a closed paren, then I guess this can represent the portion of the parse that was successful up to this point and be returned. And I just want the flow of things to include that if an error happened, that you stop and don't make any forward progress. So I suppose that means after any one of these gets called, an error check has to be occurring, right? And then we'll just do it like super basic for now, which is I guess we'll set an error setter function. Going to need the arena and the parse context, and we'll do parse error arena context, and then you also get the opportunity to write a message. And so the message here is going to be expected close parenthesis. Okay. And then I don't know if the base layer I've got right here is equipped to help yet, but arg, EA list args. I think we're gonna want this. Straight push F is what gets copied here. So it's arg, straight push FUV, arena format args, that gets the args, that gives me the result. I don't want that. That's the string. And then this is gonna like go in the context as the error. So we're gonna be like error is set to true, and then error message equals the string. And then the idea is we can just say like just keep the first error, you know, something simple. If context error equals 0, then we do all the work, right? So we just need a copy of this function in the base layer over here. And I gotta take out some of the overcomplicating details. Just use the one from the C standard, but we need now in all the examples to go include standard arg. Okay, and what I'm going to do is say from now on, forget that stuff. Examples base age is just going to have those right up at the top. Like first thing, no more of this. Changed my mind on this one this time. Different examples, I think, because there's so many separate little programs. Okay, so now you're going to get an operator ID instead of an operator kind. And oops, I just never write the dot dot dot. Isn't that the name? Is there a different one? Is it this? Okay, cool. Progress. So this one also returns a result. Skip white space. What do you got? I think you want me to check the kind specifically off of the token. I see. Yes. What else you got? Yes. Return result. Totally. What you got? Token index. I see. Here you want me to check the kind specifically. Parse error F. Okay. Right, so I need you to give me a error and error message, please. Something else I might do, just while I'm here doing this, is like do like an error offset. error token index, maybe. And that'll just be like, we just save, see if this gives us everything we need. We just save the token we're on when we encounter an error. Okay. So here you have to do if context error, then you're not allowed to make any forward progress here. So go to done. Okay, so now when you do an operator, what you do is you check for leaf. Interestingly, the question arises, why would I skip white space here? The first thing I'm going to do is check for a leaf. The leaf is going to skip white space. And then check a token. So I don't need to skip white space here. Maybe I can just do Parser leaf here. And I give you Marina in context. And you give me back the leaf. And then what's going to happen... Maybe that's just the result. And then what happens is you have this for loop. It's like, okay, I see we've got the first piece. There's still this logic that's if the context has an error, then you go to done. Right? That's not gone. But, now in the loop, what you do is you go, okay, I've got my result ready. Is there an operator coming up next that could keep this chain going? And so what you do is you check. Yeah. You check if what you've got next is an operator. Although, before you can do that, you also need to skip white space. So, there. And then you say check the next token. If we've got an operator, we keep going. So if not, we'll break. Right? Now, if you do have an operator there, then we want to see if it's one of the operators that we know about. So far what I've done is I set up this idea that the operators are being built later on. So it's kind of it's not necessarily your highest performance parser in this sense. What we would have to do to make this better is we'd have to say that this information is available and built in here so that when we are generating operator token kinds, we actually figure out their operator IDs then and sort of save that up ahead of time. Right now I'm not bothering to accelerate and move that up the chain like that, so it is going to be kind of not as impressive, but it sketches out the way that the symbol set needs to work to get the thing up and running. So what I mean is here, if I get this far, I've got the kind of token I want. I want to get the operator text, which will be the range that you get from the texts from the beginning of the token I think I might grab that token right here. And then do a token position. I'll just do it like this. Okay, right. So token position, token plus 1 position minus token position. So there's a position for the pointer and the size, right? And so I just need to make sure my base layer has that. That should do it. That's a pretty nice way to set that up, huh? I've never done it that way before, but I like it. Okay, so there you go. Wait, I didn't do that right. This was supposed to be like this. There we go. That's the idea. Okay. There we go. So then what has to happen is like a lookup to figure out the token ID from the operator text. Right? And that I'll stick in slightly separate layer here. Let's put that there. There's the parser. Here's the operators information. And I will start to consider moving this up to the top. And then what we'll say is, okay, so you set up your precedence, you set up your operators, and then there are operator functions like operator ID from operator text. We'll say from string just to simplify and sort of generalize a bit. Yeah, and then there's the string, right? And so this could come up here and be like this. And for now, this will be the worst possible one, which is for site each ID exp operator ID operator, so let's call that op sci address from ID, exp operator ID, if, and then we need a match function if this token string matches your string, then operator ID equals ID, break, return operator ID, right? And then we can put in, like right here, we want to bake an accelerator ahead of time for this path, right? We want to bake an accelerator ahead of time for this path. So that's stuff to do, but operator ID from string is up and running. Straight match is not in the base layer yet. So stick one in right here. We'll go sort that out real quick. Okay, I should do it, but I might not actually have thought everything through before I ran. So let's see. Give me my system monitor. Applications, who's. Why can't I see all the applications here? Like, oh, applications is different from processes. Right. Expression parser, there you are. End process, yes. There we go. Okay, so grab that. Okay, now you've got an operator ID. So what do you do when you have the operator ID? Well, the most basic thing we could basically say here is the right starting point, but it doesn't end correctly, but it gets us started. So the idea is, take this super literally. We've got a leaf. We've got ourselves an operator ID. If the operator ID is 0, then we have an error. Otherwise, we can fill in so what we do otherwise is we save the left side, which was the thing we had before, right? So we're making this. We had our result, which was from parsing the leaf. Now we found out we have an operator. So the leaf we put in the variable call result is not the full result. It is just the leaf. And so we're going to put that into the left side leaf. And then we're going to get the operator information we just got out of the way. So we go context token index plus equals 1. And then we ask for another leaf. And so there we go. exp parse leaf arena context. Okay, Now, if that comes back with an error, then go to done, as I've been saying. But besides that, what happens with its output? Well, its output tells us how to build a new node. And I'm going to do that first, even if there was an error, because you still returned it to me. And so I'm still going to build a structure out of it. Parse node 1. Result kind equals parse node kind operator. Binary, I think it's just operator and it's inside of a next list right now. Result kind equals op dot. Now what's in that part of the structure? I don't remember. Operator ID, that makes sense. And child 0, child 1, well that's left and right. There we go. Right, so left and right went there and there. Operator ID there. If there's been an error, get out of here and parse the ID, parse the operator goes here. And then right here we consume the operator and parse the next leaf and join the leaves together into the result. And now that's almost everything. I'm gonna print this, but this is wrong. And it's wrong because it doesn't do precedence. What we then need to do is say that while this logic is all good and fine, if you always assume that every operator sees the same precedent and left to right, that's not always the case. So let's implement in the rule that if the operator you see next needs to go before the operators that have already been applied or would be applied, that you don't fold it in the wrong way, right? We'll take a look at how that needs to work with an example once we have looked at how it's coming out wrong first. So let's go do that. So it should respect the parentheses in the example, but not any of the operator precedence stuff. That's the thing. So we should be able to print it. Add another helper here, exp parse node print, exp parse node, and then we just look at each parse node. I think we're going to want to keep track of our indents level as we go as well. Do it like this. This should be a good way to do it. Indent. Okay. So parse node. There we get our kind, and we'll switch on it again. I guess we don't really need to do it this way, right? This is a little much here, because what we really end up wanting is two big cases. So we'll just do it by hand. Operator, leaf. Maybe this shouldn't have been an X list like the other ones. Oh well. So then what happens is printf, first of all, the spaces from the indent That should do. And then printf the name operator and a colon, and then give us the name of the operator and then a new line. That should do it. And we'll come back for that part later. Then we recurse down node print. Let's see here. This would be the node op child 0 and the indent +1, and then the second child with the indent +1. Okay. And then if we get a leaf, we just go, well, the leaf doesn't have its token index, so in order to print this, I still need to have all of the dependent information too. So that becomes a bunch of pass through. And then the way we print this is we go, first we're going to form a new string by going straight text string plus tokens dot tokens bracket node leaf dot token index, except it'll be easier if I just grab a token pointer, so I'll do it that way. Token position, and then token +1 position minus token position. Right. So that gets me my string, and then I go printf and new line u32 string dot size string dot str. And now I need to go in here and get exp operator sci, let's just call this one op, address from ID, exp operator, the ID is the node op.operator ID, and then I put the op token stir size token stir, and then you need the text, the tokens, the root, and the initial indentation, segmentation fault. Okay, let's see if we can resolve that. Build slash expression parser, run. Where are we at? What's the node look like? Give me the backtrace. Frame 1. What's this look like? So the root is empty. So let's put a breakpoint at exp parse run list. Next. Step into that one, list. We got here. The context doesn't have any errors. It's all clear to 0. Good. Token index is 0. Good. Okay. And there's 53 tokens. This all makes sense. Okay. So, let's step through this. where we step into parse leaf. Switch on the kind. Token index. Token index plus equals 1. Good, that makes sense. No errors here, so if we see white space, we skip it. We do. Now, next MC is not an operator. We're done, but it is. So we get a token. And then we get the token text, which is a plus. Then we ask for the operator ID, which is a 3. So it's not a 0. So we consume the operator token. We save left and right. Context doesn't have an error. So when it went and did parse leaf just now, presumably it found an ID num 2 and returned that back to me. And now I have it in right. And then I build result up, operator ID left, right, and there's been no error. So we go back to the beginning of the loop, we check for white space, we find some, we skip it. The next thing we find is got a 2, so an operator, right? And it grabs the token, grabs the operator text, which is an equal sign, grabs the operator ID, which is a 1. Yeah. Okay, so we're up to the plus right there. Just going to keep eating through all of these all the way up until the equal sign. So I'm going to put a breakpoint at expression parser.c colon 164, and I'm going to continue until I hit that again. And I'm going to print the operator text again. I'm going to continue, and I'm going to print. I'm going to continue, and I'm going to print. I'm going to continue, I'm going to print. I'm going to continue. So this is where things are going to get interesting, actually. So maybe I will step through just to be sure I don't miss this part. Left. Okay. Now you say parse a leaf. Let's step into that. And you're going to do white space, switch on the kind. This time we found an open paren, we consumed it. So we're right here. And so we parse an operator now. And let's go into that. Okay. We're once again at this breakpoint. But now we're inside here. And if we look at the back trace, we get, this is the second layer of the operator recursing that we are on now because of the open parenthesis, right? So the open parenthesis has kicked off a nested layer of operator chaining. and it comes through here. It doesn't see white space. I'm curious, what kind of token it does see? A closed paren. So that's what I thought. It's now at this spot, right? If we look at this string as the suffix of the string from a little earlier that was left to consume, this is the part we are now at. So what has happened is it's consumed an open parenthesis, it's consumed an operator chain, and here it should be discovering that it's at the end of an operator chain. So the next thing it does is break out of the loop, return that result, and then here we're back inside the spot with the leaf. We just got back the insides of an operator chain, right? So now we're expecting a closed parenthesis. There it is. Everything works out. Okay. So now we're back in the parse op from the beginning, and we just got back a new right expression. The reason it took so long to get a right expression for this was because the whole right expression was contained inside of a parenthesis, which had an expression within it. So now that we're back from that, we can build the next node in the chain up above, and then we skip some white space, and yes, we just continue back to that spot again, right? So now if I look at p operator text, I'm seeing that we grab a star, so I'll hit next here. But here we're going to go into the parentheses again. I bet it's going to work. It hits this on the equal sign, right? So if I print the operator text here, I get the equal. And so then I'll step out. Let's finish this level. We're now at the leaf that represents the parenthesized group that we were stepping inside of them. So we haven't finished consuming the closed parenthesis, but that should do it. And now we're here. We have a new right again, right? We have the right side. And then we're going to go, okay, so let's fill in a result node. Token index. So here, let's see, up, 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 up. We were here. We went through the rest of the closed paren. I think we should be now at this equal sign. Not quite sure. Yep, there we are. Okay. So then consume that. We get the leaf for the D. Consume all of this. We check. Is there white space? No. Is... Okay, so one thing that's kind of weird, if we're at the... So this does break, right? And so we've got the result. Oh, it just doesn't return anything. We just didn't finish it. Okay. So all of that was working, except at the very end, I just don't link this to this correctly. There we go. So if I do that now, I get this. And we can see, if we look at this, the logic by which it's assembling all this. So at the very root, it's got an equal sign between everything else and D. So it's saying this is the root of the tree, and this is the right-hand side, and everything else makes up the left-hand side. Then it's saying, of all this, this is the root, with this as the right and this as the left. Its right side here is this, so equals is the root with x equals c, right? But its left is all of this, so that's all of that. And this is the equal sign at the root of that. Its right-hand side is an operator a plus b. Its left-hand side is all of this, right? So then the rest of that is the plus times equals plus plus equals plus plus times equals plus plus equals plus, right? They match. And this is the CBA 1 2 CBA 1 2 CBA 1 2, right? All that lines up. So that all makes sense. That all seems to be right, considering that we didn't implement operator precedence. I think I'm going to pause this level here, pause this project here for now, and on the next step, I kind of skipped the recursive descent manual version and went straight for this. Probably because I just figured, honestly, I'm going to get bogged down in doing so much. And here I am, over almost an hour and a half in, and it's not even doing the precedence part yet. And so probably a good call. Let's expect next time I will do precedence table version to the completion so that this arranges itself correctly based on both left to right versus right to left and the operator precedence levels of these operators. And then we can look at some of this other, I guess we skipped all the way to this. Right. Then we'll do some more advanced stuff, but I need to finish this up next time.